So let's look at the definition of expected value from your textbook. And by looking at the definition, it will also give us a good idea of how we're going to find it. The expected value is the sum. Let's stop. That means we're going to be adding some things. The sum of the products. Let's stop. Product means to multiply. So what are we adding? We're adding things that have been multiplied together. The sum of the products of each outcome so when you think about each outcome, we think about all of them. We're thinking about the sample space again. Each outcome and its probability. Okay, so let's let you finish writing first. Let's pause a minute. You guys were waffling a little bit at 15. A couple of you said you might play at $15. One of you said you for sure wouldn't. So let's put $15 in there and see if it would actually make sense for you to play the game or not at $15. So to figure the expected value, we're going to do exactly what the definition says. Let's see what it says. It talks about each outcome. So on any expected value problem, here's what I'd suggest. Make a column for all your outcomes. We're going to call those X's. Okay, now what else do I need? I need each outcome and its probability. So we're going to create another column, and for each one of those outcomes, we're going to list their associated probability. We're going to call that P of X. The next key word in our definition is the word products. So we want to multiply those. So we'll have X times P of X. We want the product of each outcome and its probability. And the last key word in our definition is the word sum, and we want the sum of all those things. So in other words, once I get this X times P of X column, I'm going to add them down here. And whatever this sum is, that'll be my expected value. Okay, so is everybody ready? Everybody done writing everything you need to write? Are we good to go here? Okay, so let's go back first to the problem and figure out what our possible outcomes are. Okay, well, let's see. We could lose $4 or lose $6 or win $3 or win $15. So minus 4, minus 6, plus 3, plus 15. That's everything that can happen. I could lose 4, I could lose 6, I could win 3, or I could win 15. Okay, now we want the probability of each of those now. So let's go back and see what the probability of those are. I lose 4 if I roll a 3 or a 5. So that's got a probability of 2 out of 6. Let's see, I lost 6 if I rolled a 1, right? So that's 1 out of 6. I win 3 if I rolled a 2 or a 4. So that's 2 out of 6. And I win 15 if I roll a 6. So that has a probability of 1 out of 6. So there's each outcome and its associated probability. Okay, it's really all over but the shot now. All we got to do is crunch a few numbers here. So I'm going to take each x times its p of x. So negative 4 times 2 sixths. Negative 4 times 2 would be negative 8 sixths. By the way, I'm not going to reduce that because if I keep it in sixths, I'll actually keep common denominators. So that'll be nice for me here in a moment. Negative 6 times 1 sixth would be negative 6 sixths. 3 times 2 sixths would be positive 6 sixths. And 15 times 1 sixth would be 15 sixths. So if we add that column now, what do we end up with? Negative 8, negative 6 is negative 14. Negative 14 plus 6 is negative 8. Negative 8 and 15 is 7. So we actually have an expected value of 7 sixths. And if you change that to a decimal, that's basically approximately $1.17. So if you played this game, say 500 times, you would come out approximately $1.17 ahead per play. That's what the expected value means. So you'd actually, at $15, you'd come out considerably ahead. And the more you played, the more ahead you would come out. Now, that doesn't mean you're going to win every time. Sometimes you're going to lose $4. Sometimes you're going to lose $6. Sometimes you're going to win $3, and you're only going to win 15 one out of every 6 times. But that's going to, because that number's so big, it's going to account for these smaller losses. So you'd actually come out ahead. Do you think the casinos know the expected value every time somebody pushes the little button on the slot machine? Yeah, listen, you don't walk in and see chandeliers there because they're losing money. So they know exactly. If you tell them at the beginning of the day how many games are going to be played and what games they are, they'll know exactly what they're going to make at the end of the day because of expected value.
They're required by law to make that public knowledge too, like what the expected win rate of each machine is.
Oh yeah? Do they have to post it like on the little machine as you're playing?
I'm not sure. The only reason I know it is because I was actually reading an article where the like video game companies kind of have like where you can buy like random things for a game and you get random things. And some states are pushing to make them where they have to do that too. They have to publish the odds of winning.
That's interesting. Well, let's look at a couple more example problems to get a little bit better feel for this stuff. But let me tell you, an expected value problem is always going to be the same notion. List the outcomes, list the probabilities, multiply those, add those. Hey, one last thing on that last problem that I should have mentioned. The expected value to play that game was $1.17. That's also known as the fair price to play the game. And here's why. If you had to pay $1.17 to play the game, then both the house and the player would come out even. No, there would be no winners and no losers over the long term. So if you're asked for the fair price, you're just looking for the expected value, really. Okay. Example 4 says in a certain state lottery, a player chooses 3 digits in a specified order. Leading digits may be 0, so numbers such as 021 and 003 are legitimate. The lottery operators randomly select 3-digit sequence, and any player matching their selection receives a payoff of $600. What is the fair cost to play this game? In other words, what's the expected value? Okay, so let's list the possible outcomes. Those are x's. And their associated probabilities, that's p of x. And we'll have x times p of x. And then we'll add those, just like we always do. Every time, that's what we're going to do. So class, right now, this is not a math problem. Right now, this is a reading problem. So we have to read carefully. So I read the problem once, kind of got a feel for what they were asking for, but I don't remember what all the possible outcomes are. So I'm going to have to read it again and see. The second sentence says the lottery operators randomly select a 3-digit sequence, and any player matching their selection receives a payoff of $600. Okay, so what are the possible outcomes? Well, I can win, which means I'm going to win 600, or I can lose, which means I'm going to win 0. Now we got to find the probability of each of those, which means we got to think about all the different things that can happen if I have 3 digits in sequence. So would repetition be allowed then? Yeah, it would be. They said you could have 003. That's a legitimate entry. So I'm going to draw blanks. And the first blank could be any digit 0 through 9, so that's 10. The second blank could be any digit 0 through 9, so that's 10. And the third blank could be any digit 0 through 9, so that's 10. So there's 1,000 different things that can happen. How many of those would be a winner? 1. So your probability of winning is 1 out of 1,000. So your probability of losing is the other 999 out of 1,000. Okay, let's multiply. 600 times 1 over 1,000 would be 600 over 1,000. 0 times anything is 0. And when we add those, I get 600 over 1,000, which is 60 cents. Now what does that mean? That means the expected winnings per player, per person who plays the game, is 60 cents a player. Now the way that's divvied out is one of them's going to get 600, and 999 of them are going to get 0, but that means they average 60 cents a play. So the fair price to play that lottery would be 60 cents. If the state charged 60 cents to play it, they'd break even. If they charge $1 to play it, the state's going to come out 40 cents ahead. So on and so forth. So expected value is very applicable to game theory. Now it's also very applicable to insurance. And while we're here, I might as well throw this out. If you're a person who finds this stuff interesting, and there are those out there, I kind of find it interesting myself. The people who figure expected values are called actuaries. So if this stuff's very interesting to you, this is a great career. Most years, if you look at like the top 25 jobs in the country, you're going to see actuary a lot of times in the top 10 based upon pay and stress level and all that stuff. It's not an easy career. There's a series of tests you have to pass to become an actuary. And then even once you become an actuary, there's more tests. Usually it ends up being about 10 tests you can take to end up making it to the bigger salaries. But actuaries work for insurance companies. So they would take, say, all college students and crunch the data on how much it costed to the insurance company for all the repairs for all college students. And then from that, they would decide, well, what do we need to charge a sophomore in college if we want to make X amount of dollars? They also figure things like how much do you have to give out of your check to a pension fund so that that pension fund's going to be solvent by the time you retire. So obviously they haven't done a very good job of that in the state of Illinois with a lot of the pensions there, and the politicians need to quit raiding the pension funds. Now the pension funds are hurting and they're costing the state lots of money, and it's just a big mess. So I don't think they listen to the actuaries. But that's the kind of work actuaries do. They figure probabilities and then expected outcomes as far as dollars and cents usually. A lot of times private companies will even hire their own actuaries to see what an insurance company should be charging for, say, a group health insurance plan or such as that, so they know when they go to bid it out to companies about what they should be looking for and if they're getting ripped off and that sort of thing. So that's a great career if this stuff is interesting to you. It's not easy to get there, but it is a good career. So I want to finish off, and I don't know if I have time to get all the way through it, but we're going to try it anyway. I want to finish off with example 9. See what time. What have I got, about 7 minutes? Yes, about 6 minutes actually. Okay, let's read. Jeff Marcellus, a farmer, will realize a profit of $150,000 on his wheat crop unless there is rain before harvest, in which case he will realize only $40,000. The long-term weather forecast assigns a probability of rain of 0.16. An insurance company offers crop insurance of $150,000 against rain for a premium of $20,000. Should Jeff buy the insurance? So what we're going to do is we're going to figure Jeff's expected cost with the insurance, expected value with the insurance, and without the insurance. That's how we're going to do it. So let's do it first without the insurance. So again, we're going to look at each outcome, call that X, its associated probability, call that P of X, multiply those, and add those. So what are the possible outcomes? Well, it could rain, or it could not rain. If it rains, the problem told us that he's going to get $40,000 out of his crop. But if it doesn't rain, he'll get $150,000 out of his crop. So those are the two possible outcomes without insurance. Okay, the probability of rain is 0.16. So the probability that it wouldn't rain would be 1 minus that, 0.84. Okay, so if we multiply those according to your book, 40,000 times 0.16 is $6,400. And 150,000 times 0.84 is $126,000. So his expected value without insurance is $132,400. Now what does that mean? That means if Jeff had, say, 100 fields with this exact same scenario, he would expect to come out ahead $132,400 per field. Some of them he'd come out ahead 40,000, some of them he'd come out 150,000 ahead, but on average he'd come out ahead 132,400. Okay, now let's do the same analysis with insurance. Well, we got the same two possible outcomes as far as it could either rain or it wouldn't rain. Now, let's figure the rain first. Okay? If it rains, he's still going to get his 40,000 that he was going to get anyway. Plus, he's going to get the $150,000 insurance premium. Payoff. But he's going to lose the $20,000 that it cost him to buy the insurance. So if you take 40 plus 150 minus 20, you're going to get 170,000. That's what that ends up being. Okay, if it doesn't rain, he's going to get his 150,000 that he was going to get anyway, but now he's out his 20,000 in premiums for the insurance. That's what it cost him. So the probability of rain is still 0.16. The probability of not rain is still 0.14. And according to your textbook, if you multiply across here, you're going to end up with 27,200. And down here, you're going to end up with 109,200. Which gives an expected value of 136,400. So his expected value, if you made the decision based upon this analysis, it would say buy the insurance. And probably if he had several, like I said, 100 fields with this same, he's probably not going to have 100 fields, but if he had a bunch of fields with the same scenario, he'd probably buy the insurance. He's going to come out ahead per field. Okay. So, one of my favorite sections of the semester, the expected value section. Here's your assignment on page 619. Let's take 5 through 14 as the assignment.